Hello everyone. Welcome to the second part of our bipolar junction transistor lecture. In this lecture, we'll talk about some advanced concepts regarding the BJT's operation, specifically its IV characteristics, current voltage characteristics. So without further ado, let's get started. We'll start with some modes of operation for BJT, and then we'll discuss the amplification process. And subsequently, we'll talk about some secondary effects that we observe in the BJT's characteristics.
Without any loss of generality, we will stick to NP and BJT if not specified otherwise, because it's all the same to talk about NPN or PNP. Now, if we look at an NPN BJT, this is emitter, this is base, and this is collector, and you could clearly see that we have two PN junctions back to back, and the base emitter junction can have a voltage across it, which we will mark as VBE, and the collector base junction will have a voltage across it, which we will mark as VCB. And depending on what type of voltage we apply to this, we could either have forward biasing or reverse biasing. And there could be four different combinations for these two junctions. So if you look at the possible combinations of VCB and VCE, you could have forward bias, cutoff, inverse active, saturation. So from a high level perspective, if the emitter base junction is forward biased and base collector junction is also forward biased, so both of these are forward biased, then we have what's called the saturation mode, like this. And if emitter base junction is forward bias, base collector is reverse bias, then we have forward active mode. If both of these junctions are reverse bias, then we have cutoff mode. So the only option left would be base collector forward biased and emitter base reverse bias, then we have inverse active mode. And we will have a closer look at it when we discuss the the four scenarios that you see here. We will see what happens to the minority carrier distribution for these four different combinations, four different scenarios for biasing. So let's start from the forward active mode. Now, I will quickly go through these four different scenarios, and then I will use the next slide to review this with some emphasis on some important aspect. And that's why this empty white space is there, so that I can draw. Okay, so forward active mode. So this is emitter, base, collect. Let me try to use okay, that's fine. So emitter, base, collector, and this is the base emitter junction, this is the base collector junction. And remember, in a forward active mode, emitter base junction will be forward biased and the base collector junction will be reverse biased. So I'm just writing it down here. And because of the reverse biasing, you see the base collector junction is wider compared to the base emitter junction. Okay. And there are even more prominent signature of forward and reverse biasing. And that's exactly what we are going to talk about now. So the dashed lines that you see here, this line, and this line, they represent the thermal equilibrium minority carrier concentration. And what is that? Think about an emitter, which is N-type. In an N-type material, electrons are the majority carrier. So we say that we have an abundance of electron in N-type material. In P-type, we have an abundance of hole. So holes are the majority carrier. And N-type electrons are majority carrier again. Now, when I say that we have an N-type material, that means we have abundance of electron. That doesn't mean there are no holes. In any type of semiconductor, you have electrons and holes, but depending on the type, you have one or the other as the dominant species, right? One of the types of carriers will be the majority carrier. So for N, we have electrons. For P, we have holes as majority carrier. But in this particular figure, what we are looking at is not majority carrier concentration. We are looking at minority carrier concentration. So in the N-type material, you will still have some level of holes available. So P represents the number of holes or concentration of holes. E stands for the emitter region. So PE, number of holes in the emitter region, and 0 simply indicates that it's thermal equilibrium. And just recall that thermal equilibrium means you haven't applied any external voltage or anything. Okay, if you don't apply any external voltage, then you'll have this level. But are we operating in thermal equilibrium at all? How do you know? Remember, we are talking about forward bias and reverse bias, right? As soon as we start speaking in terms of biasing, that means your thermal equilibrium is no longer the case. So yes, these levels are there had we been operating in thermal equilibrium level, but we are not. We are operating in regular scenario, and that's what we will talk about. We will see what happens to this minority carrier concentration in non-equilibrium scenario. By the way, before we get to that, let's also quickly look at the other zones. Look at the base. So we have holes as majority carrier because this is p-type. So electrons will be minority carrier. That's why we have electron concentration in the base terminal, and 0 means thermal equilibrium. So that is the level of minority carrier that we have in the base. And similarly for collector, which is n-type, we will be having holes as minority carrier, the opposite, right? And holes in the collector region, thermal equilibrium, and you have a different level. Now, you might have noticed that, hey, the minority carrier levels are higher in the collector and lower in the emitter. Why is that? That actually relates to a fundamental approach to designing BJTs. If you remember correctly, collector is the least densely doped zone in a BJT. Okay, so it is least densely doped. Base will have higher doping density compared to the collector, and emitter will be the highest, will have the highest doping density. So oftentimes, if you remember, we represent this as N and this as P plus, even though remember I mentioned that this doesn't represent degenerate, it just represents that you have higher doping concentration. And we represent emitter as N plus plus, just to represent that it has even higher doping concentration compared to the base, and obviously compared to the collector. So whenever you have a very high majority carrier concentration, the minority carrier concentration will reduce accordingly. So the highest majority carrier concentration will lead to the lowest minority carrier concentration, and the lowest majority carrier concentration will lead to the highest minority carrier concentration. Okay, and just see if this checks out. uh, I'm having trouble with the pen for some reason, but it's okay. See, this guy, the collector, has the highest minority carrier concentration because it was the least densely doped. Least densely doped means it had the least levels of majority carrier electrons because it was not doped high enough, right? And because of that, it had higher degree of minority carrier. So all of these lines have meaning. And now maybe we can take a moment to go through these four figures, and you see this scenario will show up every time because that's related to thermal equilibrium, zero applied bias. So it doesn't matter what type of biasing you're applying, forward or reverse, these levels will not change, right? This level will remain the same. That's what we should keep in mind. Now, the changes that we'll see will be uh, in the distribution of minority carrier in non-equilibrium condition, and that's what these blue lines are for. These blue lines that you see, they represent what happens in non-equilibrium condition, meaning when you apply external bias. Now, like I said, you have applied forward bias here. Remember one thumb rule, and that's logical, obviously. When you apply forward bias uh, to a junction, the concentration of minority carriers will go up, will increase beyond the thermal equilibrium level. So it's simply uh, similar to creating more minority carrier at the junction. And when you apply reverse bias, the concentration of minority carrier will reduce below the thermal equilibrium concentration. That means whatever you had at zero bias, you'll have more than that when you apply forward bias, and you will have less than that when you apply reverse bias. Now let's try to examine whether that is the scenario here. This is forward bias, and this is the thermal equilibrium level. And you see at the surface, at the emitter base junction, you have higher than what you had at zero bias because you have a forward bias, by the way. And that's not only true for the N region, that's also true for the P region. See, whatever degree of minority carrier you had, now you have more than that, much more than that, because you have forward biasing. And by the way, how did that happen, right? How did that happen? when I talk about minority carrier, these lines, remember, these are minority carriers. In p-type material, minority carriers are electron. But where did these extra electrons come from? They actually came from the emitter region, N region. So N region had an abundance of electron. When you applied a forward bias, these electrons, you know, went to the base region, and then they were marked as minority. They were majority carriers within the emitter region, but when they go to the base, they end up becoming the minority carrier now. But you see, most of the electrons who migrate from emitter all the way to the base will be near the surface, near the emitter base junction. And the farther you go inside the base, let me clear it off again a little bit. The farther you go from the surface inside the base, there will be recombinations occurring because you have an abundance of holes here in the p-type material. And the electron, when they try to move inside the material, there will be higher chances of recombination, and gradually the concentration of electrons will diminish. So the farther you move away from this junction surface, the lower will be the concentration of minority carrier. Okay, and same thing happens here. So this is the concentration of holes which actually came from the p-type material, p-type base, and the highest level of hole concentration will be at the surface. And the farther you go inside the material, this is n-type material, so you'll have an abundance of electron. These holes will gradually recombine with the electrons, and they will recombine, and that's why you see a gradual reduction of the concentration for holes. So the same logic. Now, if you don't want to remember anything else, just remember this, that when you have forward biasing, the concentration of minority carrier at the surface will go above the thermal equilibrium. See, that's the case for both of these scenarios. And it will gradually diminish all the way up to the level of thermal equilibrium. It's as if as you go deeper into the material, the effect of these excess carriers will not show up, right? The material will behave as it is in thermal equilibrium. That's why it will almost merge with the thermal equilibrium concentration. However, let's consider what happens in the reverse bias condition, right? We have talked enough about this base emitter junction, which is forward biased. So you have more than the thermal equilibrium concentration at the surface, and gradually as you go inside the material, they will diminish towards the thermal equilibrium concentration, but they will never go below that. That's important. Now, let's consider the base collector. Oh, sorry. The base collector junction, which is reverse biased. Now let's start from the collector end. So since this is reverse biased, we will have less than the concentration of minority carrier in thermal equilibrium. So it's almost zero, as you see here, because of reverse biasing. And the point is, it's not only that the collector part is reverse biased, this base collector junction is reverse biased. So this part of the base will also be reverse biased. And that's why at this point you have less than the thermal equilibrium concentration for the minority carrier. So the reason why you see the reason why you see this crossover point here is because you have forward biasing in this edge, but you have reverse biasing in that edge. The forward bias will try to keep this concentration above or at least equal to the thermal equilibrium. And this guy, the reverse bias scenario, will try to keep it below the thermal equilibrium or at least equal. Okay. And in doing so, you have a delicate balance. And because of that, you have this crossover point. And I think it will be easier when you see a saturation mode, because there will not be confusions like this. Now, don't worry, we'll get back to this forward active mode again, because this is the most important mode that we use for BJT. Just take a second look at the reverse biasing in the collector end. So because of reverse bias, you have less than the thermal equilibrium concentration. And as you go deeper into the material, it will gradually reach the level of thermal equilibrium, but it will never go above that. That's the signature of reverse biasing. Now, let's look at the cutoff mode. That's again easier, right? These are thermal equilibrium levels, and with respect to these levels, we will be drawing the non-equilibrium concentration. So we have both of these junctions, emitter base and collector base collector, reverse biased. So when the emitter base junction is reverse biased, the concentration here and here will be less than what you had in the thermal equilibrium level, and they will gradually try to be equal to the thermal equilibrium concentration. Let's look at the collector end again. This is the thermal equilibrium level. The minority carrier concentration will be lower compared to the thermal equilibrium level. And as you gradually go deeper into the material, it will try to match with the thermal equilibrium level. But in the base, you have reverse biasing here and you have reverse biasing here. So this edge will try to gradually merge all the way to the thermal equilibrium level. And the other end will also try to gradually merge to the thermal equilibrium level. But since both of these ends are reverse biased, well, you will not be able to ever reach the thermal equilibrium level. So it will go up and then it will go down again. That's what you see here. Okay, because both of these are reverse biased. And let's look at another example, the saturation mode. So in these scenarios, both of these junctions, emitter base and base collector, are forward biased. And that's what you see here. Emitter base junction both will have higher than the thermal equilibrium concentration for minority carriers. And this guy will try to gradually reach at this level, the thermal equilibrium level. By the way, base collector junction is also forward biased. So in the collector, you'll have more concentration of minority carrier than what you had in the thermal equilibrium. And then it will gradually try to match to the thermal equilibrium concentration. Now, base is interesting because it has more than thermal equilibrium in this end as well as in this end, right? Because both of these junctions are forward biased. And essentially what you see here is a gradual change without being equal to the thermal equilibrium concentration, because both of these ends are forward biased. All that's left now is the inverse active mode. So this is literally the inverse of the forward active mode. Okay, so let's start from the base collector junction, which is going to be forward biased. So you have more than the thermal equilibrium concentration here. It will gradually try to reach the equilibrium concentration as you move further into the collector. Emitter junction is reverse biased, so less than the thermal equilibrium concentration. And then as you go deeper into the emitter, it will gradually try to match with the thermal equilibrium concentration. And the base, this junction is forward biased, so you have more than the thermal equilibrium. This junction is reverse biased, you have less than thermal equilibrium, so a gradual change from here to there. Okay. So interestingly, we can observe almost all of these modes of operation in a BJT. It's not like we have different BJTs which demonstrate different modes of operation. The same BJT can operate in different modes depending on how much voltage you're applying, how much current you're providing, and we will talk about that in few minutes. But here is another slide which has the exact same two figures, forward active and saturation, just in case I needed to draw anything, right? So I wanted to, we have used some already, uh, you know, or maybe like ready-made figures, I would say, to talk about these details. So I thought that it might be easier for you to kind of grasp if I draw everything from the scratch. Okay, that's why these empty white spaces are there. White space is there. So let's imagine, let's try to draw a BJT. This is the base emitter junction. This is the base collector junction. And I'll have to keep in mind whether I'm drawing a forward active mode or reverse active mode. So if I try to draw a forward active mode, then this emitter base junction will be forward biased and base collector junction will be reverse biased. That's why you see I have used a thicker uh, depletion region compared to the base emitter junction, which has a thinner depletion region. Okay, because reverse biasing will increase the width of the depletion region. Now I'll draw the thermal equilibrium levels, thermal equilibrium concentration levels. So remember, emitter will be the most, will have the highest level of doping. So we'll have, say, this much minority carrier concentration in thermal equilibrium. And for base, we will have, say, slightly higher, this much minority carrier concentration in thermal equilibrium. For collector, say, we will have even higher, this much thermal equilibrium concentration in, minority carrier concentration in thermal equilibrium. Now, let's also write down the notation, right? So the minority carriers in emitter, which is n-type material, will be holes. So I'll denote that with P to represent holes. And this is in the emitter region, and this is at zero bias. So PE0. And then this is base, which is p-type material here. So this level will be the concentration of minority carrier electrons. So N in the base region at zero bias. So NB0. Just check if these are matching with what we used before, right? And then in collector, which is a p-type material, n-type material again. So the minority carriers will be holes. So I will define this region as concentration of holes in the collector region at zero bias, PC0. Okay. Okay, let me clear it off a little bit. Let's start fresh again. So emitter base junction, base collector junction. Okay, emitter, base, collector, different levels of minority carrier concentration. Now, let me change the pen color to make it easier to follow. See, now this is forward biased. That means our minority carrier concentration will be more than what we had in the thermal equilibrium level, and it will gradually diminish all the way towards the thermal equilibrium concentration as you move further into the emitter, further away from the junction. For the base, same thing, because what happened to it? Got erased somehow, so let me draw it again. So for the base, we still have forward bias, right? So we will have more than the thermal equilibrium concentration here, so higher concentration. And I will draw that later. I haven't drawn the entire thing, but it will gradually diminish. That's what you surely know. But where it will eventually go, we will see that in a second. But let's go to the collector now. So you have reverse biasing here between base and collector. So if the collector has reverse biasing, its thermal equilibrium concentration, its minority carrier concentration will be less than the thermal equilibrium concentration. So it will start from here and it will try to gradually reach the thermal equilibrium level as you go deeper into the collector. For base, it should start from here because, again, reverse biasing. So in the base terminal, this end starts here and this end starts here, right? Two different ends. So all you have to do is probably just connect them. So you'll have a crossover point somewhere in the middle of the base. Okay. So there you go. You have this particular figure of forward active mode. So I hope that makes sense. I hope you'll be able to draw that yourself if need be. These figures are really good indicators to what goes on in the BJT in terms of the device characteristics. And we will probably use at least this forward active mode figure once or twice as we move further into the discussion. Okay, so moving forward, we are ready to look at the current voltage characteristics of a BJT now. Okay, and I will come back to this particular slide, but I will use some empty white spaces to talk about that. And after we are done, I will get back to this particular slide and we'll try to make sense of the stuff that we're looking at. Okay, so just have a look at this circuit, and what I will do is I will redraw that in the next page. But let's look at the main aspects of it, right? We have an NPN BJT, and the one in the middle is always the base, right? We have base here, and this guy is this guy is emitter, and this is collector. So collector, base, emitter, and then you have a resistance at the collector end and resistance at the base end, and you have input voltage here and here. Okay, and just look at the emitter current, collector current, and base current. So we have lots of different stuffs. Let's get back to, we will come back to this figure. uh, Let me just clear it off for a second, and then let me draw that here. So we have N, P, N. Let me also write emitter, base. Oh, I meant to write, this is collector, base, emitter. it's all the same, right? We have to be careful because collector and emitter, they are both n type. So if we don't connect them properly, we will have a different type of connection, by the way. Okay, so there are different ways of connecting a BJT. Based on that, we have three different modes: common emitter, common base, and common collector. We'll look at the other connection topologies in later part of the course when we talk about BJT based circuits. But common emitter mode is the most popular connection because of good reason. We will talk about that now. So let's see how we make a common emitter connection. So you have a resistance at the base terminal, say RB, base resistance, say, and then you have a voltage source like this, say. I'm just putting something randomly. And emitter, so your base voltage is taken with respect to emitter. So this is maybe the ground. Okay, so with respect to emitter. Now, as for the collector end, we have another resistance, which is the collector resistance, and then we have a voltage source again, and then this is also connected to emitter. So this collector voltage is also with respect to emitter. So emitter is the reference for determining the base voltage as well as the collector voltage, right? We are taking emitter as the reference. That's why this is called a common emitter. I mean, there are different ways of looking at it. So this part of the circuit that you see, right, if you follow the arrow, this is called the input of the BJT, input circuit of the BJT. And the other part that you see here, this is the output circuit of the BJT. No matter which circuit you take, input or the output, you will see emitter always remains common between both of these circuits. So emitter is common between the input and output part of the BJT. That's why it's common emitter. It's common between input and output. Okay. And remember one more thing. Let me use the eraser to clear it off a little bit. So otherwise it will become too clumsy. Okay. Yep. So now we are ready to look at different biasing scenarios that might occur in a BJT. So this is a voltage source which will be dictating as VBE, base emitter voltage source, and this will be VCE. So we will be varying. I shouldn't be calling it as complete VCE because VCE will be this voltage, the voltage between collector and emitter. So this is X, this is Y. So VXY will be VCE. Okay. So let me use a different name. So this is VCC and let's call this VBB. Okay. The base emitter voltage will be, so this guy P and say this is Q. So voltage between these two nodes, P and Q, will be the base emitter voltage. Right. I don't want to confuse you with too many notations. Let me again clear these things off. Okay, forget about XY, right? All right. And we are ready to look at. Let's first talk about the input circuit because that's easier. That's much easier to follow. So what we have here is, for a second, just think in terms of the voltage that we're applying to the base and emitter terminal. So this is the base emitter voltage. So when you try to plot VBE, base emitter voltage, IB versus VBE, base current versus base emitter voltage, the relationship that you get is called the input characteristics of a BJT, because you're just dealing with the input circuit here. Okay. Now, interesting thing, just forget about the collector here. Just look at this portion of the BJT. Isn't that a simple PN junction? So when I talk about base emitter voltage, I'm applying a voltage across this PN junction, and depending on whether it's forward biased or reverse biased, we will have characteristics which is similar to the diode, right? And remember, we are looking at a forward active mode. Forward active mode, meaning the base emitter junction is forward biased. So VBE that we are looking at is given in a way that this PN junction is forward biased. Okay, if this is forward biased, then the IV characteristics for this guy, the input circuit, should be similar to the IV characteristics, current voltage characteristics of a regular PN junction diode. And that's why I have some, auxiliary slides. Like I said, I have some auxiliary slides ready. I'll and these slides are taken from some of the lectures that we have already covered in the course. I just wanted to remind you, rather than telling you to go back and see those slides, I thought that it might be easier if I have the slides within this special lecture. So there you go. Within the auxiliary slides, the first one that I want to talk about is this ideal PN junction current density. Just to remind you, so by the way, this was current density, but current density and current will be exactly similar. So see, this is forward bias. In forward bias, here is how you see, here is how the current voltage characteristics looks like, right? Actually, this is too ideal. Practically, I mean, you have to apply much higher voltage to turn on the uh, PN junction, because there are some voltage losses that occur in the PN junction. Okay, so, and reverse biasing, remember, you have a constant level of current in reverse bias. That's almost equal to the saturation current. You have a constant level of current in the reverse bias, right? In forward bias, the current gradually increases with the voltage. And try to relate to it. VA is the voltage across the PN junction, and I is the current through the PN junction, right? With respect to the voltage across the PN junction. Now, going back to our discussion, when I try to draw VB, so draw IB, which is the current flowing through the PN junction, with respect to VBE, which is nothing but, so this is VBE, right? Which is nothing but the voltage across the PN junction. So I should see a characteristic similar to the diode like this. And that's exactly what I see, what we see as an input characteristics. This is called input characteristics of a BJT, because again, you are looking at just the input circuit. Now, there is a catch. See, even though it looks like a PN junction, but there is another terminal which will definitely interact with the PN junction that we're dealing with in the input circuit, that's coming from the collector. And we will also have to see what happens when you apply different levels of collector voltage to this BJT. Now, say for this graph that we have drawn, maybe this was for a specific value of collector emitter voltage, say. So we have a collector, we have an emitter, we also have a voltage across the collector emitter side, as you see, right? Collector emitter side. So this graph that we have obtained, maybe this was for, say, just taking some number as an example, say VCE was 1 volt. Okay, for VCE of 1 volt, we had this graph. Now, what happens when I increase VCE? Let's consider that. So turns out if you have 10 volt of VCE, your maybe that means more than this, the graph, the same graph will look like this. So your current will reduce actually. So for VCE equals say 10 volt, again I'm taking some random numbers here just to demonstrate the point. Whenever you increase VCE, this graph, this current will reduce. See, you have much less current now than what you had before. Isn't that counterintuitive? You're trying to increase a voltage, but you're increasing a voltage, but current is reducing. No, it's not counterintuitive. Let's see why that might be the scenario. Remember one thing, we are talking about the base current here, which is flowing like this, right? That is the base current. And remember one more thing, emitter current flows here, collector current flows into the collector. Into the collector, emitter current flows out of the emitter, base current flows inside the base. And remember this relationship that emitter current is equals to IB plus IC, base current plus collector current. Just to remind you of that. Now, the reason why increasing VCE reduces the current is this. Now, I think I should probably clear off this uh, figure a little bit, but I want to keep this here. So what I will do is I'll go momentarily go to the next slide, which is a empty slide, and I'll try to draw something here. So we are dealing with this in P in BJT, and in P and BJT we are looking at a base emitter voltage, and we are looking at the base current. Okay, simplified picture. And when I say collector emitter voltage, I'm looking at something like this, and collector current and emitter current. Now what happens when you increase the uh, collector emitter voltage further? See, I'm already applying a positive voltage here, and with respect to this guy, this base is negative with respect to collector. By the way, with respect to collector, base is negative. So essentially this collector base junction is reverse biased. And remember, that was the purpose in a forward active mode. We have talked about it many times. The collector base junction was supposed to be reverse biased. Now when you apply your VCE, that means this voltage across the entire stack, you essentially will increase the voltage across VCB as well, right? Your VCB will also increase, because VCE will give, I mean, a part of VCE will go across VCB. So when you increase VCE, you will have higher VCB as well, collector base voltage. By the way, collector base voltage is a reverse bias voltage. When you increase VCE, your VCB increases. So increasing VCE will lead to increase in VCB, which is the collector base voltage, and that is a reverse bias voltage. And imagine what happens when you increase the reverse bias further, right? When you increase the reverse bias further, any idea what happens? Let me explain. I will need to draw a much larger BJT here. This is the emitter, base, and collector. I've intentionally tried to make it larger. Now let me use a different color here. Say, let's consider that for a regular collector base voltage, which is reverse biased, you have this much width, for say VCE, VCB of 1 volt. Let's consider something, right? 1 volt. That's the reverse bias voltage, by the way. Reverse bias voltage. Okay. Now, when you apply a higher reverse bias voltage, say VCB of 2 volt, again. Now let me try to use another color to make it clear. The depletion layer width will increase further like this, and what that will do is the following. So in a NPN BJT, by the way, this junction is forward bias all the time, so you have a thinner depletion layer width, right? Now in a BJT, what ideally happens is electrons from the emitter goes inside the base, and then they diffuse gradually and goes towards the base collector junction. Okay, again repeating, electrons from the emitter goes to the base region because of the forward bias, and then when they are inside the base, they gradually diffuse all the way to the collector, and when they reach the collector, the electric field in the base collector junction grabs them and then uh, zaps them inside the collector region because of the electric field. If you remember correctly, in a PN junction we have an electric field within the space charge or depletion region, not outside the space charge region, right? Only within the space charge region we have electric field. And let me help you recall this. See, that's why I have so many white pages, empty white pages. see, this is the depletion region of a PN junction. Okay. Uh, say in the depletion region, you have, let's consider that you have positive charge and negative charges. Oh, let me, I probably should have drawn it with different colors to represent that these are depletion regions. So you have, say, positive charge and equal amount of negative charge here, and because of that you have an electric field. Now once a hole goes all the way to the uh, depletion region, the electric field works on the hole in this direction. So it throws the hole like this in the same direction as the electric field. But as for electron, when the electrons try to flow all the way to the surface, the electric field pushes the electron in the other way, in this direction, okay, pushes the electron in this direction, opposite to the hole. But remember, wherever the hole flows, the current flows in that direction because these are positively charged particles. But wherever the electron flows, current due to the electron will flow in the other direction because electrons are negative charges. But just note the direction of the electron flow. Right now, for the NPN BJT, collector, base, emitter, collector was n type, this was p type, and this was n type. Now electrons from emitter goes all the way to the base, and when it reaches the base, it will gradually diffuse towards the base collector junction because this is forward biased, right? Flows of electrons and holes are permitted. So electron will flow from emitter to the base and it will try to diffuse all the way towards the collector. Now here is where the action happens, that near the collector you have a depletion layer, and let's try to find out the direction of the depletion layer. Again, uh, the electric field of the depletion layer is in this direction for a reverse biased base collector junction. So whenever the electron reaches, this is the electric field, whenever the electron reaches at this node, this edge of the depletion region, they are grabbed by the electric field and they will uh, go inside the collector very fast, driven by the electric field. Okay, and they are only grabbed by the electric field whenever they arrive at the uh, space charge region. Before arriving at this region, they will be just diffusing gradually, gently through the base. Now the reason why I wanted to go to that much detail is because otherwise it's not really that intuitive to understand why increasing the reverse bias voltage reduces the current, base current, by the way, base current. Okay, so imagine, just think about, ask yourself this question, whether it will be good for the conduction from emitter to collector. Mind the notation, current flow from emitter to collector, whether it will be good for our current flow from emitter to collector if the reverse biased region width increases. That means you have stronger reverse bias. Will that be beneficial or not? Here is the answer. Again, common sense. Emitter, collector, base. Imagine if you have a thinner depletion layer like this, electrons from emitter goes inside the base, and then this is gradually diffusing all the way to the collector. Okay, now compare that with if you have a thicker depletion layer like this, thicker depletion layer, that means more powerful reverse bias, then the electrons should have already gone to the depletion layer and they would have had been grabbed by the electric field already, and they would have had gone inside the collector. So the flow of electron from emitter towards collector becomes easier if you have a stronger reverse bias in the base collector junction, right? Does that make sense? The base collector junction will widen the reverse biased depletion layer, and the depletion layer will be able to catch the electrons from the base earlier, and they will be able to, more efficiently let the electrons flow inside collector. Remember, the longer it takes for the electrons to go to the collector base junction, the higher will be the chances of recombination, and you will lose a lot of electrons through recombination within the base. Okay, so again, trying to draw a clear picture here. Emitter, base, collector. When the electrons go inside base, if it spends a lot of time inside base, there will be higher chances of recombination, and you will lose a lot of electrons coming from emitter to the base before they can manage to go inside the collector. But by widening this space charge region, by applying a stronger reverse bias potential, you are actually grabbing these electrons from the emitter earlier, even before they can manage to, recombine within the base. So all you have done is you have increased the number of electrons that can successfully flow from emitter to collector. How? By increasing the strength of the reverse bias in the base collector junction. Well, right, it might sound counterintuitive that, hey, I'm increasing the reverse biasing, so that should discourage the current. But remember, you are reverse biasing the base collector junction, but the current or electron flow is originating from the emitter end, not from that end, not from base collector end, right? It's originating from the emitter end. Once they are inside the base, they have no way but to diffuse towards the base collector junction, towards. And once they reach at this junction, then the electric field takes over, and the electric field pushes the electron to the other end, to the collector. Okay, so the thicker the base collector depletion layer will be, the more uh, now let me use another notation. The more electrons from emitter will be able to go to the collector, and the number of electron flow will be directly related to the current. So more of the emitter current will go to the collector, more of the emitter current will go to the collector. Just think about it, right? Now remember this notation: IE was equal to IB plus IC, right? If IC becomes almost equal to IE, the closer IC gets to IE, IB will become less. Let's take some numbers. Say IE is, say, 100 microamps, say. IC is 95 microamps, because maybe number of carriers were lost while transiting through the base. So base junction will be 5 microamps. Now you see the math, right? You could easily add this up. Now what if IC becomes more efficient? It manages to take in more electrons from the emitter. So now it becomes 98 microamps. So 100 microamps came out of emitter, say, and then 98 microamps was seen in the collector. So 2 microamps can only come from the base to make sure that this relationship still holds. So your base current will definitely have to reduce, simply because your emitter current and collector current are getting closer to each other. Okay, so when you apply a stronger reverse bias at the base collector junction, that actually helps transfer of electrons from emitter to the collector. I hope that makes sense, that that eventually reduces the base current. Remember, you are talking about the base current in the input characteristics. So going back all the way to this particular slide where we were talking about the input characteristics, and we talked about what happens when you have a higher collector emitter voltage. Again, this is a messy figure, but I hope you remember what we talked about. This is collector, this is emitter. When you have larger collector emitter voltage, just compare this 10 volt with 1 volt, right? Larger collector emitter voltage will provide larger voltage across the collector base junction as well, right? that means you will be having stronger reverse bias, and stronger reverse biasing will enhance the efficiency of electron transfer from emitter to the collector. That means collector current will become almost equal to emitter current, will be closer and closer to the emitter current. And that also indicates, that will indicate that the base current will have to reduce, because the total sum of these currents will, have to maintain KCL. So when IC becomes nearer to IE, IB will have to reduce. And that's what you see here. IB, this is IB, by the way. Just notice that this input characteristics plots IB. So for higher VCE, for higher applied, voltage VCE, you have lower IB. So let's draw another line here. Say for VCE equals, say 20 volt, that means even higher, you have even lower base current, right? Okay, so bottom line, the IB versus VBE characteristics, also known as the input characteristics, will look like this. Let me draw a few lines here again. Now, these graphs will will represent VCE increasing. So as the VCE increases, these graphs will shift to the right, and the current for a given VBE will have less current for a higher VCE. That's what it's trying to convey. Okay, and this is called input characteristics, by the way, because we have so far talked about only the input circuit. We haven't even talked about the output circuit, and we will get there right now. So before going there, I'll have to clear up. If I leave it here in the slides, it will anyways not make any sense, right? This is super you know disorganized. So let me go and clear all of this off. And now we are ready to go back and look at the output characteristics. Okay, we will look at the output characteristics. So I will do the exact same thing. I will again draw this so that I could draw over them. N, P, N. This is emitter, base, collector. Okay. For the time being, I'll not even draw the resistors and character pairs separately. What I will do is I will just for simplicity, again, this is collector, emitter, base, right? This is base. I will just talk in terms of VCE and VBE and IB. So current IB, imagine you have, some sort of voltage that you apply, and you get base emitter voltage here, VBE. And then you get collector emitter voltage here, from the output. So you apply something here. I'm just trying to simplify the figure further. Okay, now I'm going to draw. Let me ask you, what is the output voltage here? The output circuit will see the collector and emitter. Emitter is common between input and output, by the way. So the output voltage will be VCE. That's the variable. That's something that we could control. We could control the VCE, and the current that we should look at will be the output current. Actually, current flowing through the output portion of the circuit is IC, collector current. Okay, so we will be plotting IC over IC by IC versus VCE. Okay, IC versus VCE. Now, remember, remember one more relationship that we learned in one of our previous lectures. That was beta, or common emitter current gain, was IC over IB. Okay, we had this, we discussed why that is the scenario, that is the case, but that's a fundamental equation for BJT. So in other words, I could write IC equal to beta IB. Beta is usually in the orders of, say, 100, 200, or something like that. So if you have 1 microampere of base current, you have, say, 100 microampere of collector current. Okay, now let's consider that for, by the way, this is VCE, and when you apply a positive VCE, just try to look at this NPN junction again. Let me probably just focus on that part. NPN CE. Okay. When I say VCE, I'm putting positive voltage here and negative voltage here. So positive on the N terminal, right? Positive on the N terminal represents reverse bias. We have been talking about this over and over again, right? So we have reverse biasing in this terminal, this NP junction that you see, collector base junction. We have reverse biasing there. Now, when you have higher and higher VCE, the higher the VCE is, the higher will be the reverse bias. Okay, because remember, VCE could be divided into, let me write it down here. VCE will be the voltage between the VCB, collector and base, plus VBE. So essentially, when you increase VCE, a part of it will also increase VCB, right? So VCB is directly the voltage across this PN junction, as you see here. So increasing VCE will further increase the uh, reverse biasing scenario. And by the way, VBE, let's consider that VBE is positive, forward biased for the time being. So we apply a VBE that ensures that this junction, base emitter junction, is forward biased. Let's start from that, forward biased. Now, when you apply high enough VCE, what's going to happen? Your IC will become maybe a constant times beta. So here is, say for example, let me start taking some number. If you apply maybe IB equal 1 microampere, this is corresponding to IB, by the way. Okay, for 1 microampere of IB, you will see, say, 100 microampere of IC, simply because, say, your beta is 100. And see, this is a linear relationship. So beta will be, sorry, IB will be multiplied with beta and you'll get IC, done. As long as you ensure that the base emitter junction is forward biased and base collector junction is reverse biased. And that's easy when you have a higher VCE, because the higher you go, you will definitely have reverse bias and the reverse bias will become stronger. That's it. Okay. And remember, in reverse bias condition, just to remind you one more thing, that's why I will go back to the auxiliary slides again. In this slide, in reverse bias condition, before it breaks down, no matter how much voltage you apply, how much reverse bias you apply, you have, a constant current. Doesn't matter how much reverse bias you apply, you have a constant current, simply because it is dictated by the space charge region, the electric field of the space charge region. It's not dependent on anything else. Okay. So you are dealing with a reverse bias scenario here in this junction with respect to VCE. That's why this will ideally remain fixed. And the level of IC that you'll see will be directly related to how much IB you provide. If you provide 1 microampere IB somehow, by the way, I'm talking about providing a current, and that's exactly same as providing a voltage and adding a resistance, right? This resistance and voltage source will eventually create a current. And that's why I decided to simplify it with IB. Let's take another example. If you increase IB to 2 microampere, say IB to 2 microampere, for 2 microampere, you will have, 200 microamperes of IC, say 200 microampere, because your beta remains the same. Okay. And for, say, IB equals 3 microampere, you have 300 microamperes of IC, and so on. So it's as if with IB, your IC will linearly increase. See, this is more like linearly increasing in steps. Okay, keeping the same ratio beta. Now, you might have noticed that I haven't been drawing the VCE below a certain level. And there is a reason for that. When VCE becomes small, right? When VCE becomes small, the reverse bias that we used to get across the, let me actually change my pen color here. that way it will be easier, because there are too many markings. Let me use red. So when VCE becomes smaller below maybe certain levels, then the PN junction, which was previously reverse biased, may not be reverse biased. It might not have enough reverse bias voltage across it. And why is that? Right? Imagine, just remember, there is a base voltage. Okay, let me say that the voltage was, say, at this particular point it was 1 volt. Let me take a random number here, right? 1 volt. And your base VC was, say, 5 volt. Now see, the voltage across this PN junction will be effectively 4 volt, and this is plus this. I don't know if it is becoming clear. Let me go to one of these empty slides. Okay, N P N, this is base, and let's consider that somehow you applied 1 volt here and you had 5 volt here. Okay, so positive 5, positive 1. So with respect to this guy, the overall voltage across the PN junction will be 4 volt, and this will be plus, this will be minus. Okay, so reverse bias, still reverse bias. Now if you convert this 5 into 10 to 10 volt, you will still have reverse bias, and even higher reverse bias. Okay, reverse bias, which is good, right? So that's why when you increase VCE, nothing changes. You still have reverse biasing, and once you have reverse bias, the current will always be the same, and that's what you see in a regular diode as well. Now let's have a look at what happens when the VCE becomes less than 1 volt. Say if your VC, instead of being 5 volt, if it becomes, say, 1 volt, that means it has reduced below a certain level. Now you see, you effectively have 0 voltage across the base collector junction. That means you are no longer having a reverse biasing. Now if it goes below that, say for example, instead of 1 volt, now you have 0.5 volt. Now you actually have a forward bias, right? You actually have a forward bias uh, in the base collector junction. Now you had forward biased here in the base emitter junction was forward bias. Now your base collector junction can also become forward biased when your VCE becomes lower, and that's what you see here. Below a certain level in this zone, VCE is so low compared to the base voltage that we get, that eventually the collector base junction becomes forward biased as well. Okay, and once you have forward bias, then the current responds with the voltage, and that's what you see. The current gradually responds. Lower voltage, lower current. See, lower the voltage, lower current, because this is forward bias. It's just behaving like a forward bias diode. High, on the other hand, higher voltage, higher current within this region, by the way. If you increase voltage, your current will increase gradually, but up to a certain point. After that, you will again have reverse biasing in the collector base junction, and it will, stabilize. There will not be any more changes. Now there could be a confusion here, which I want to clarify. Remember, so far we started, let me change the color of the pen again, started talking about this section first, right? The flat regions. And we talked about how the, oh man, it looks super messy. I mean, let me clear it up a little bit so that I could at least write something within this slide. Okay. Okay. So I was trying to tell you is that within this region, our collector base junction was reverse biased, and base emitter junction was forward biased. Remember what mode this is? This was forward active mode, right? So we have been working in forward active mode during this flat portion of the IV curves. But Remember, for lower VCE, we were no longer able to keep the reverse bias on the collector base junction. This collector base ended up becoming forward biased as well. So you have forward biased for both of the junctions, and both forward bias represented what? Forward bias, saturation. But forward bias, reverse bias, called forward active mode, right? Now, here is where the confusion may arise. So this region, the green region of these graphs that you see here, these are the saturation region in terms of the mode of operation for the BJT. We could say that the BJT is operating in the saturation mode. But I mean, we obviously, let me draw a random variable, say velocity versus electric field, say, and maybe as the electric field increases, the velocity of a particle increases, and at some point it will no longer increase with electric field. So we say that, hey, the velocity has saturated. Whenever a quantity becomes flat like this, we say that it has saturated, right? Say when we look at the current voltage characteristics, and we see that, oh, it is no longer responding to the voltage, we say that, hey, the current has saturated. So this is saturation for the current, but it is not saturation mode for the BJT. The saturation mode for the BJT will occur within the smaller VCE section. So this is saturation mode of the BJT, but that's not saturation for the current. The saturation for the current is here. Okay, so oftentimes, this term becomes very confusing. And what you are seeing here in this particular figure, now I guess we are ready to look at this figure. uh, uh, by the way, I hope you understand why there are so many different lines, because you have increasing IB, and that's what we did here. For different values of IB, you have different levels of IC. IB and IC are directly linearly related. Now, and these are flat lines because you have reverse bias junction, and here you have forward biasing at lower VCE. Let me clear it off again. And you see this region is saturation mode, and this is forward active mode for the BJT, forward active mode. One mode left, which I haven't talked about. I'll talk about that in a second. But I hope this, at least up to this much, makes sense. Now, a very simple scenario would be, what if your, so far we have been assuming our base emitter junction is somehow magically forward biased. If that is the scenario, then these graphs are all valid. But if for some reason you reverse bias the base emitter junction as well, right? If you reverse bias this base emitter junction, reverse biased, that means you simply just put a 0 volt at the input, done. You have, right? Or maybe some negative voltage at the input. You'll have a reverse biasing at the base emitter junction. Then you'll not actually have any current at all. Okay. Or you'll have very negligible current. That is represented by, let me draw that line here, maybe a flat line. I mean, it's difficult to show on the axis because it will not show up. It's more like a flat line. And that is the signature of cutoff mode. So you see, cutoff mode is literally nothing. When you don't have anything, that's cutoff. That's it. So that was simple enough, I guess. And that's what you see here. This tiny little region that you see, that represents cutoff. It's not even there. I mean, it's on top of the axis. Okay, so cutoff mode and forward active mode and saturation mode. And reverse active mode is actually exact opposite of the forward active mode. And had BJTs been symmetric devices, say this N and this N were the same, then forward active mode and reverse active mode could have been the same thing, right? But you should have already seen that BJTs are not really made as sandwiches like this. They are, they have complicated 3D geometry, and because of that, forward active mode and reverse active mode will have differences in characteristics. And we designed the BJTs in a way that forward active mode should be, should provide us the best operation. So reverse active mode will give us degraded performance. So you don't want to operate in reverse active mode, by the way. Okay, so having said all of this, I'm ready to, clear off this empty white pages again, erase all ink, because we'll need to talk about one more thing. That is, oh, in this slide, let me clear it off again, erase all ink. So, so this is IC versus VCE characteristics, which is called the output characteristics, because you're dealing with the output of the BJT. Now, we are ready to look at one final thing about this graph, which is, this dashed line that you see. This is called a load line. And why is that? That is related to the load resistance. Remember, the resistance that we see in the output, this guy, RC. This is related to the resistance that we have in the output, because turns out that resistance has a significant role in the overall operation of the BJT circuit. And we'll talk about why that might be the scenario. Okay, let's just quickly look at these simple expressions. Okay, let me clear it off again. VCC, which is the applied voltage here, will be dropped across two things. It will be dropped across the resistance, and it will be dropped across the collector emitter junction. Collector, the entire stack, entire material, entire stack, right? The voltage, input voltage, will be divided into two parts. So RC will take a voltage equal to ICRC. That's the voltage drop across the resistance RC. And, VCE could be divided into VCB, collector base, and VBE, base emitter. So VCB and VBE, done. And then eventually we could write it as VCE, right? Doesn't matter. And ICRC could be represented in a simpler way as VR, resistance voltage drop, done. Now, if you take these two expressions, let me just write it here. VCC equals IC, oh, I don't know what happened. Okay, sorry about that, probably. Okay, so ICRC plus VCE, right? This is a simple expression. Just remember this expression, and I will write it here. VCC equals ICRC plus VCE. Let me just put it right there for a second. Now let's pay a little bit more attention to this resistance, right? To this resistance, and try to draw the current voltage characteristics of this resistance. So far, we have been drawing the current voltage characteristics of the BJT, but this resistance is also a part of this entire, circuit. And let's for a second try to draw the current voltage characteristics of this resistance. And I would like to remind you of very simple geometry, high school geometry, right? Remember, y equals mx plus c, this type of equations. This is the equation of a straight line, and this is how it looks like. This is c, by the way. This is y-axis, this is x-axis. Wherever the straight line has an intercept with the y-axis, that is c. Okay, this is c, and m is nothing but the gradient, right? Gradient. If you have a positive slope, the line looks like this. Negative slope, like this. Okay, so negative slope, this is positive slope, right? We know that. Okay, now let's try to see what type of equation this is. And again, we are trying to draw the current IC versus VCE, using the same equation, which is actually for the resistance. This is an expression that relates the resistance as well in the overall picture. Don't worry, the BJT is also here within VCE, right? Collector emitter voltage. The BJT is also there, and now we are also considering the resistor here. It's not like the BJT is the only thing that's there. BJT is also coupled with the resistance. That's why we have to consider these equation. Now, in the y-axis you have IC, so your y should be IC. In the x-axis you have VCE, so your x should be VCE. So let's try to arrange it this way. Y, so I can rearrange it as ICRC equals VCC minus VCE. So let me divide with RC on both sides. So you have IC, you have IC equals minus 1 over RC VCE plus VCC over RC. Okay, just simple, rearrangement. Now, this is Y, this is X, because X, Y. Okay, I'm gonna plot that right here. And then what is that? This should be M. Compare that with the equation of a straight line. Y equals mx plus this is C. And notice that the gradient or the slope is negative. So our straight line should look like this one, like this, right? So you should have a straight line like this, which should relate to the resistor, to the resistance. Okay. And now going back to this particular figure, see this dashed line that you see here, that represents the IC versus VCE characteristics for that particular resistance that we are dealing with. Okay, I hope that makes sense. Now, here is one very important point that we have to keep in mind. Let me clear this figure off. This IC that you see here in the figure, it is flowing through the BJT, right? That's true. But it is also flowing through the resistance. So it is impossible to have two different ICs, one flowing through the resistance, one flowing through the BJT, because they are in series. So you should have the same current flowing through both of them. Now, when you maybe draw, remember solving equations using graph? You have one straight line, you have another straight line. Wherever they intersect with each other, that will be the solution of the system, because at that point, both of them agree, right? Now, when you draw, let me again clear it up a little bit. Okay, so when you draw the current voltage characteristics, IC versus VCE for a BJT, right? And then you draw the current voltage IC versus VCE, same characteristics for a resistor, for the resistance that you see here, resistor. Whichever point they intersect, that point should represent the point of agreement between the resistance and the BJT. That means that will be the IC that your overall system will be able to sustain. Okay, so remember, when you have a resistance coupled with a BJT, they will both interact together and decide on a specific IC. And here is the important part, interesting part. See, in this particular figure, the point of intersection occurs where? In the saturation mode of a BJT. In the saturation mode of a BJT, right? Saturation mode. But for an amplifier type operation, it's better for us to make the BJT operate in forward active mode. That means we would love to have an intersection, here, as you see, right? For these particular characteristics, you have an intersection at the saturation mode, which is not good. But if you turn your attention to this particular line, then you have an intersection at the forward active mode, which is good, very good. And how can you change from, say, this is X and say this is Y? How can you change from X to Y? By changing the base current. That means you will have to apply that much base current to ensure that your overall system operates in the forward active mode. You see that? And then you can reduce the IB further to, push this point further deeper into the forward active mode, right? Which is good, by the way. Okay, so you can control that using IB. That's the important part. See how cross coupled this entire scenario is. You have so many different knobs to play with, right? And there is one more knob, by the way, before we finish talking about this aspect. That is, the slope of this line is also an important factor. I know this is becoming messy. I mean, the figures become messy so easily. Now, the slope of this line, if you change the slope of this line, say from here to maybe like this, then also you can change the operating points. And how can you change the slope of this line? Let's go back to the drawing board again. The slope of this line was related to what? RC. You can change the RC. You can use different resistance values to kind of selectively change the slope of this line from here to here to here. That's another knob, right? These are interesting stuff. And the circuit designers, whoever designs circuits with BJTs, definitely keep all of these things in mind, and they design the circuits. Now, before we conclude, by the way, the line that we have drawn, the straight line, this is famously known as the load line. And you might have seen that, you might have hopefully understood that the point of intersection is a very important point, because that dictates the overall solution for the system. Okay, so this much will be the final uh, collector current done. Now this point is usually mentioned as Q point, quotient point, Q point. Okay, Q point. This is a famous popular notation that people use. So for example, hey, I want my Q point to be here. Say I want my Q point to be here. So you either design this line in a way that it goes through this Q point. Done. Okay, that's another example. Okay, so that concludes our discussion on the output characteristics of BJT. And now we are ready to look at how a BJT can act as an amplifier. So we will use technically the same circuit. See, resistance, you have voltage, everything remains the same, but one thing. That is, we have an additional input voltage source here, which is an AC source or alternating source. Okay, this is an input VI. The reason why other voltage sources are there is because we will ensure that we have properly set up the mode for the BJT. We have used this input voltage, this output voltage, to make sure the base emitter is in forward bias and base collector is in reverse bias. That means we are operating in the forward active mode. We will use these DC voltage sources to do that. And then on top of that voltage mode, we will impose a new small signal. Why small signal? Because if this signal is strong enough to disrupt the forward and reverse bias, then you'll have no idea how the BJT will operate, right? You are not in control anymore. You don't know which one is forward bias, which one is reverse bias. That's why the concept of small signal. We will not use that high of a signal to disrupt the entire forward and reverse biasing. So this voltage is low enough or small in terms of amplitude that it doesn't really change the overall forward to reverse biasing. Okay, that's dictated by the DC voltages. Now this is the input voltage which we try to amplify. So imagine you have a voltage which has very low amplitude. Okay, say I don't know, maybe say 1 volt, or maybe say 1 volt. Okay, you have 1 volt of amplitude in the input AC voltage. Now, this input VI will create an input current, input IB. Okay. If the voltage is sinusoidal, IB will also be sinusoidal. By the way, there will already be an IB which is corresponding to this voltage and this resistance. Remember, in the previous circuit which we talked about here, we didn't have any AC source, but we still had IB, right? You have a DC voltage and resistance, you'll have a DC IB. So here as well you have a DCIB, but on top of that you have an alternating version as alternating part as well. So if you try to plot IB with respect to time, if you only had a DC component, DC voltage, then IB would have been like this, straight line, DC. But now IB will actually be like this. So on top of the DC, you will have an AC portion. Okay. So shifted DC kind of thing. So that's what you see here, IBQ. By the way, Q is there to represent that you have designed the overall system in a way that you have chosen your Q point. You have chosen your Q point accordingly, wherever you wanted it to be. And then on top of that Q point, you have imposed an oscillating input signal, right? And that's what you're trying to amplify. You're trying to amplify this VI, by the way. Okay, so your IBQ will be, oscillating on top of the DC bias that you had before. Now, here is the important part, interesting part. For IB, we know that beta is IC over IB, or IC equals beta IB from the BJT operation, right? So whichever IB you have, it will be multiplied by the gain of the device. If it is 100 times, beta is 100, IC will be 100 times. So whichever amplitude you have in the base current, you'll have maybe beta times amplification in the amplitude of the collector current, right? Because of this relation. So your collector current will be amplified simply because of the correlation between base current and collector current. Now, interesting, if the collector current is enhanced by beta times, the collector current is flowing through this resistance, and the voltage drop across this resistance will be IC times RC, the voltage drop across this resistance. So the voltage that you see across this RC resistance will also be enhanced because you have amplified the current, resistance remains constant, so your voltage drop will be enhanced exactly by that amount beta. Okay, so you have provided a minuscule amplitude, tiny amplitude of input voltage, oscillating alternating input voltage, and at the output you're getting an amplified version of voltage simply because of the current amplification. You have actually amplified the collector current, and that collector current has led to a voltage drop which is higher in amplitude. So your output will have to be taken from where? Your output will have to be taken from this resistance RC. That's why this resistance is very important. And input will be this one. So this is input, this is output of your amplifier. Done. There you go. This is how a BJT can amplify an input signal. And by the way, this is a signature of common emitter configuration. In common emitter configuration, you have this type of a scenario. That's why this particular mode of operation is the most common, because you want to design amplifiers. These are useful stuff. Okay, so that concludes the discussion that I wanted to have within this special lecture. I hope you have understood what I tried to explain. If not, please never hesitate to reach out to me with questions. I'll be more than happy to schedule one-on-one sessions if required. If not, you can always drop by during my office hours and ask me questions. So good luck. Thanks again. Bye.
So in this slide, we'll take a deeper look at different components of the current density, different current densities that we observe within the BJT structure. And interestingly, there are many components of current that shows up in a seemingly simple BJT structure that we don't always talk about, and we often ignore. We just talk about three different current components: emitter current, base current, and current collector current for the most part. But these three major components are made of some individual entities, as you'll see discussed in this part. So now let's take a deeper dive into the BJT structure and take a look at different components of currents that give rise to the eventual emitter current, collector current, and base current. And again, there is a lot of detail provided here in this slide as well as in the textbooks where I took it from. My intention is to give you a high-level overview and show you the end product and how to use the insight from this discussion for optimization and proper design of the BJT. So just pay attention to the high level picture rather than caring too much about the specific components themselves. So as you know, the primary purpose of a BGT, the primary intention is to use the emitter to inject electrons all the way to collector. Okay, and base is kind of like an intermediary, a medium through which this electron is diffusing eventually to the collector. That's why the name collector, because it's supposed to collect those electrons. Now, in between, there are other components that come and go, and that adds to or takes away from the total current. And we'll talk about all of them, and we'll see how this factor into the overall efficiency and overall gain of the BGT structure. So on your right, you see different components with explanations on the side, and I'm gonna go through them one by one just for the sake of it. There is no reason to memorize, or there is uh, no obligation on you to try to even remember all of these components. Okay, let's just try to understand this together. So the first one is J. J represents current density. As you know, we have used it many times. When you use an N with it, it typically represents current density due to electron flow. And if I put in E, that represents emitter side, C represents collector side, B represents the base junction, as you can imagine. So JNE represents the current density due to the diffusion of minority carrier electrons in the base at x equals 0. So it's a mouthful, I know. But so rather than going through all of this individually, let me try to show you from the image itself. So this is JNE, which is a current density driven by electrons. Remember, when electrons go from emitter to the base, the current should actually be flowing in the other direction according to our convention, right? As you know, if electrons flow from left to right, current should flow from right to left. That's why we are using this type of a representation to show that JNE, which is a current density, is flowing into the emitter because the electrons are getting from emitter to the base. What is the reason for the electrons to go from emitter to the base? Obviously, as you can imagine, diffusion through diffusion. So due to diffusion, electrons uh, go from emitter to base and eventually diffuse through the base towards the collector. Now, so that's one component. What's the other one? JNC. JNC is basically uh, the electron flow between collector and base junction. So one of them was between emitter base, the other one is between base and collector. What is the other one? JRB. This is basically the difference between what you get here and what you get here, JNE and JNC. And the reason for having this difference is that recombination occurs within the base junction. So base has a lot of holes because it's p-type, and electrons are getting injected into the base. Obviously, electrons and holes can recombine and eliminate each other. And when they do, that takes away a portion of the current, as you can imagine, because that takes away a number of carriers that are available for conduction. So this is treated like a current component because when holes are taken out through recombination, new holes are generated within the base region. And this generation process could be represented as an additional current component that is coming up. Okay. The other one is JPE. Let's try to figure that out. This is JPE, which is diffusion due to minority carrier holes. So apparently, as you see, base has a lot of holes because it's p-type and emitter has n-type. So there is obviously a possibility of holes diffusing into the emitter, and holes, since they are positive charges, wherever the holes flow, the current will flow in the same direction. That's why the current direction is also going to be the same as the whole flow direction. So this is another component. And so there are two junctions as well, emitter base junction and collector base junction, as you see. For forward active mode, which is the most prominently used mode for amplification, as you know, we keep the base emitter junction forward biased and the base collector junction reverse biased. Okay, so in the forward bias junction, as you see here, there is a additional current component that we see that occurs due to recombination of carriers. within the forward bias junction. So remember, there are two recombination factors that we talked about. One within the base, due to the recombination of electrons that were injected inside the base and the holes that were already inside the base. So because of their recombination, you have a component called JRB. But there is also another type of recombination that takes place within the forward biased junction between base emitter, not inside the base, it's inside the junction. So this recombination component is represented as JR. Notice we are not using E, B, or C. It's not in the emitter, base, or collector. It's within the uh, junction. Now, for the other component, JP, let's try to find where that JPCO is. This is JPCO. So this is due to the diffusion of holes in the collector. So basically, notice base and collector junction and the base collector junction, there is a possibility of having some sort of diffusion of minority carrier that you have in the collector inside the base. Okay, and because of that diffusion, the current will also flow in the same direction because it's positive charge, and that's what we represent with JP. P represents hole, and the reason why we use C is because we want to represent that it's coming from the collector. Finally, within the reverse bias junction, which is this one, base collector junction, there is an additional generation of carrier. So typically in forward bias junction, you have recombination of carrier. In the reverse bias junction, reverse bias junctions are typically wider, as you know, and within that region, it's more probable for us to generate electron hole pairs, and that generation leads to an additional current component, JG. So as you can see, long story short, obviously nobody can remember all of this. This is not necessary. We came to know about all of these components through long research, as you know. The reason why we are discussing all of them separately is because I just wanted to show you that there are many secondary components beyond the primary flow of electrons from emitter to collector. But do you like all of them? Certainly not. You would like it to be super simple. Electrons trying to pass through the base to reach collector, as simple as that. But that's not going to happen because there are multiple factors in play. So we have to define some quantities to to identify which one of these factors are actually useful and which one of them are loss factors, and that's what we are going to do here. So we identify three different factors. One is called the emitter injection efficiency, which is basically a measure of what percentage of the total injected current is due to the electron. So JNE is the current component due to electron. JNE and JPE are the total current component getting injected into the emitter, as you see. JNE and JPE, but one of them is for electron, the other one is for hole. And basically we're trying to find what percentage of it is due to the electron flow. That's why it's called emitter injection efficiency factor. One more thing, base transport factor. Notice that JNC is the current that we are injecting from the collector, and JNE is the current, electron current, that is getting injected into the emitter. So there is a difference between them because some recombination, generation, all of them will come into play. So base transport factor represent what percentage of the collector current could actually make to the emitter. So that's why this is basically the ratio between these two, the collector component and emitter component. Finally, recombination factor. Just take a look at the total current density due to electron, and holes in the emitter, electrons and holes in the emitter. And now consider the total current component, also including the recombination. So there was a recombination current as well. So what percentage of this is actually usable current and what percentage of this is kind of the total current? That's a measurement that we use to define the recombination factor. So turns out, remember in the last lecture we discussed alpha and beta. alpha for the most ideal BJT, we want alpha to be 1 or as close to 1 as possible, and beta could be as high as possible because that's related to the overall amplification factor. The higher the beta is, the more amplification power you have. Okay, and alpha should be close to 1 to give us favorable properties in a BJT. Now, turns out alpha could be represented in terms of the product of these three components, gamma, alpha t, and delta, as we have just discussed. So if you try to improve alpha or take it close to 1, you have to pay attention to these three individual components. Okay? And if you do some more maths, basically, and by the way, that's what you see here. These three components were multiplied together to obtain alpha. And you can easily prove it. It's there in the textbook, Niemann's textbook. So if you are interested, you can look it up. But I'll go to the next slide and show you how that is useful for engineers. Okay? Now, as we just discussed, this gamma, alpha t, and delta factors could be further calculated and expressed in terms of more fundamental design components. So gamma, as you see, initially we just wrote it in terms of current density, but those current densities could be further broken down into more deeper parameters, and eventually these are the final parameters that we arrive at. N represents doping concentration, NB represents doping concentration in the base, NE represents doping concentration in the emitter, and so on. And all of this, terms have been defined here in this chart. If you can take a look at it if you're interested, but I'll get to the point very soon. Give me a few more seconds. So what is D? Diffusion coefficient. What is X? That's the thickness. XB represents the thickness of the base. XC represents thickness of the emitter, and so on. Okay, so you could express gamma in terms of this foundational parameters. You could represent alpha t in terms of this deeper parameter, and similarly delta with respect to deeper parameter. So if you do so and replace all of them in this equation, you end up with this long expression that merges all of these deep level parameters together and connects them to alpha. And by the way, once you know alpha, if you remember, there was a relationship between alpha and beta. If you know alpha, you could replace that and calculate beta as well. So apparently you get two expressions, one for alpha, one for beta. Now looking at this equation, which connects multiple design variables in one easy to understand, hopefully, equation, now the engineers can come in and see how to tune these parameters to have favorable characteristics. And what do I mean by favorable? Alpha needs to be as close to 1 as possible. And what should I do to these doping concentrations to achieve that? Notice this is 1 over something. So if this denominator increases, alpha will be less than 1, which you hate. You don't want that, right? So one of the ways to do so, one of the ways to avoid that would be to reduce this denominator as much as possible. And how can you reduce it? One way would be to reduce this term, NB over NE. I hope you remember from the previous lecture that in a BJT, you have, say, NPN. That means emitter, base, collector. Emitter is typically heavily doped, base will be lightly doped, and collector will be even lightly doped. Like, I don't know, let me just use minus to represent that. Okay, so why is that? Notice if NB over NE is small, that will keep the overall denominator lower, and that will keep this alpha closer to 1. Otherwise, if this denominator is high, alpha will be much smaller than 1, which we don't want to have. So that's why NB over NE, if NB over NE is smaller, that helps. And how can you make NB over NE smaller? By making the doping concentration of the emitter higher than the doping concentration of the base. That's how you can make it smaller. So that, notice those decisions that you learned about in the previous lecture, that emitter is heavily doped, base is deliberately kept at a lower doping concentration compared to the emitter, it is directly related to this understanding from this mathematical expression. Similarly, one more thing, notice this geometry factor. This is the width of the base, this is the width of the emitter. Typically, I don't know if you caught that, emitter is, much wider than the base. If this is the base, this could be the emitter. That is deliberate because we want to make sure this is XC, this is XB. We want to make sure XB over XE, which is this factor, is as small as possible. And to achieve that, we make XB smaller than XE. So that is also a design decision that engineers derive from these complicated expressions. So it's not about, I mean, this is quite the opposite. It's not about, how you arrive at this equation. It's about what can you do with this equation. Yeah, that's what the engineers care about. Anyways, I'm not going to go through all of these steps individually. I just want to give you some pointers as to how that works and how those design decisions were made. And same thing applies to beta. You can take a look at it and you'll see that the same argument applies to beta as well. So apparently you could improve both alpha and beta by making these design decisions. Okay, so I'll move away from it, and just to also clarify that there is no need to remember, try to remember any of these equations, because if I ever test you on this, those equations will be given. Now, moving to another secondary effect, a secondary effect that we often see in a BGT structure, that is base width modulation. And as we discussed in the last few minutes, if you look at the IC versus VCE property of a BJT, ideally you expect that your collector current saturate and will be flat like this. But practically, you don't really see perfect flattening of collector current. You see a slope. There is a mild slope in the IC, whereas it was supposed to be saturated, perfectly saturated and horizontal. But why is that? An easy explanation, and I'm going to give you a high-level quick explanation for that. Imagine you have emitter, which we are not drawing properly, and you have collector here, and in between you have the base. This is the base. Okay? So in the base collector junction, when you notice, this is with respect to increasing VB. Okay? So as you are changing the collector emitter voltage, the voltage across the collector base junction also changes. And let me just use the empty space here. So you have emitter, base, and collector. So there are two junctions. This is one of the junctions, base collector junction, and the other one is base emitter junction. This one is base emitter junction. Okay. So when you change the collector emitter voltage, a portion of it leads to changes in the depletion width for the base collector junction. So this junction itself can widen as you increase VCE. It could widen, okay, because that's reverse biased, by the way. So the more voltage you apply across collector emitter, the more voltage shows up across base collector, and the wider the reverse biased zone becomes. And that's what you see here. If it becomes wider, let me draw it again. So this is emitter, base, collector. If this, imagine case A, this is case A, and now we're going to go to case B, where you have a wider depletion region. Okay, you can immediately see that usable space in the base junction has reduced. So if you have a wider depletion region in the base collector junction, you have a lower usable region in the base, so lower effective width in the base. Okay, so within the base region, that's what you see. If your spacer charge region increases, apparently your base boundary shifts and the base becomes narrower. Okay, so apparently the base width, the width of the base changes with VCB. It's not a constant, basically. So despite us considering XB as a parameter which is constant, this is practically not constant, because the depletion region in the collector base junction can change, and that leads to lowering the effective width of the base terminal. And here is how that affects the overall property. Here is how that leads to changes in the current. If you remember, in the base junction, say electrons came from the emitter, and so you have a large concentration of electron, and they gradually diffuse. Okay, so there is higher concentration of electrons here, lower concentrations of electron in the other side. And remember, since there is a change in concentration, that means a concentration gradient, there will be a diffusion from emitter towards collector, as you can imagine. Now, keeping that in mind, if you reduce the base width, this slope of going from high concentration to low concentration will be steeper. Notice that the slope has become steeper, and the diffusion current is related to the slope. If you remember this properly from our previous lecture on drift diffusion current actually cares about the gradient of this concentration. So if you reduce the effective base width, you increase the gradient. That means you increase the overall diffusion current. So as you see, that leads to, instead of having a constant base width, you have a changing base width, which gradually increases the current. And that's what you see here. This is the signature of that gradual increase in current. Instead of getting saturated, you keep increasing the current due to the base width modulation. Okay, as the base become narrower, current becomes more higher. That's what you see here. So first of all, how do you measure it? How do you measure it? You could, how do you quantify it? You could quantify it by using this expression, which is nothing but, let me just quickly show you an easy expression. Imagine you are trying to find the slope in this region. Okay, and how could you do it? Just take a tangent and see where it intersects with the y-axis. Okay, now let's pick any point here and try to make a triangle. So there is a specific VCE at this point, and there is a constant voltage which is often called VA and termed as early voltage. Early is somebody's name, by the way, who proposed this approach. So early voltage. So the base of this triangle would be VCE plus VA, and that's what you see here. And this is the IC. This is IC. So if you take, the ratio of these two, you get tan theta, which is the slope, basically, slope of this region. Or you could also take the slope by taking a derivative of IC with respect to VC, whichever is easier. Either ways, you're going to end up with a simple equation like this, where VA is the parameter that we get by taking a tangent of this, any of this line. You could take tangent from here, tangent from here. You see all of them will ideally intersect at a common point. That's why this common point is an important parameter. It's called the early voltage. And the way you figure that out would be by first characterizing a BJT to obtain its IC versus VCE property, and then taking a tangent. Again, I'm just repeating that argument one more time. And wherever that intersects the x-axis, that's your VA. And you're right, it's typically a negative voltage, which is fine. Okay, so this is another factor that we should keep in mind and update our understanding accordingly. Practical BJTs do not perfectly saturate. They keep showing a gradual slope. It's a little bit exaggerated here in this slide, as you can see, to make a point. Even if it is not that much, it is still going to be a slope. Okay, and this slope is related to the output conductance or output resistance, which we could also derive. So basically this DIC over DVCE is an output conductance of the BJT. All right, so let's move to the next secondary effect. It's called the current crowding effect. And let's look at the practical view of a BJT. Despite us drawing the BJT structure this way, emitter, base, collector, all the time, we have been drawing this because it looks simpler. BJTs are not really made by that. It's not easy for you to have materials connected to each other side by side. So that's not how we fabricate things. We fabricate things, bottom up. So meaning you first create the collector, which is the least densely doped or heavily doped layer. This is the collector layer, and on top of it, you know create a p-type base layer, and on top of it you create an emitter layer by doping over and over again on top of each other. Okay, so that's how you create from bottom up. So you have one layer, and within that layer you create a different layer, and within that layer you create the other layer. That's how you make p and p junction. That's why BJTs look like this. Now this is an emitter, this is the emitter terminal. Base terminal, as you see it, this entire thing is the base terminal. So there are two connection points, but there could be more, doesn't matter. Both of these are base, basically. This one and this one, both of these are base. And you have one collector, and there is this big region underneath. That's the collector. Now, the point is, when electrons flow from emitters to collector, or current flow from collector to emitter, whatever, they tend to congregate towards the edges of the emitter, because that's where the electric field is the most powerful typically. And you could do some math calculations, and it will show you wherever the geometry abruptly changes. So if you have material layer like this, around the edges you have the strongest electric field. So electrons will try to pile up or get inside the layer through these edges, more so than what happens in the middle. So in the middle you have very few electrons getting in. Most of these electrons will try to get in through the two edges. And that's why, by the way, this is another example of the same thing. Most electrons will try to get through around the edges, but there will be only a few trying to get through in the middle. So that leads to unnecessary crowding of electrons or current closer to the edges of the emitter, which creates reliability issues. It could heat up the emitter edges, or it could break it down at some point through high injection, because more high concentration of electron injections are occurring within a limited area, heating up that area and eventually damaging the material. Okay, so to avoid, this is called current crowding effect. To avoid that current crowding, people often use intelligent geometry in BJT design, especially for power BJTs. So for BJTs that need to provide high current, this crowding effect could be detrimental, because it could lead to dramatic heating up of the device and eventually damage it. So for that, instead of using one emitter, we break it down into smaller chunks like this. And all of these chunks are actually connected to each other. Notice these are all connected. So essentially they are one emitter. But instead of using one big layer, you use smaller layers, so that even with current crowding, there will be less of a current crowding effect than, what if you had one emitter. So imagine, let me just draw it here. Imagine you had one emitter, which is like really, really wide, and electrons are trying to get into the emitter. Most of the electrons will get in through these edges, and only a few will use this region anyways. So instead of wasting this huge area, why don't we just make it this way? So you have smaller chunks of emitters instead of one big one. And then, yeah, electrons can still prefer the edges, which they will, but the effect of wasting that area will not be as prominent as was before in the previous case. Okay, so that's a potential solution for current crowding effect. And this type of structure is called interdigitated emitter structure. From the top view, if you look at it from the top, this is how it looks like. It's like fingers crossing each other. The base emitter and collector crossing each other. That's why if you try to visualize it from the top down view, you will see something like this. Okay, finally, let's talk about the equivalent circuit model. Before discussing this, I want to have a quick recall of what we discussed in the BJT lectures. For BJTs, we discussed equivalent circuit model like this, which talked about the resistance that we assume within the diode structure, two capacitors, junction and diffusion capacitance, representing properties of the diode. So apparently, the concept of using a equivalent circuit is to represent different physical phenomena that occurs within a device with electrical analog, meaning resistors, capacitors, or inductors, or voltage sources or current sources, whatever works. Okay, so this used to be a way to solve mathematical problems or circuit problems. So you needed to represent this diode in this form using basic circuit entities so that you could do KCL, KVL, or other circuit theory based approaches. But nowadays we have powerful simulators. We don't necessarily need to always break it down devices manually to these equivalent circuits, because most of the times you have models that the foundries will make, but the foundries will at least have to break it down into smaller components, right, for you, even if you don't have to do it personally. So going back to the BJT lecture, similar to the diode, obviously BJT is a more complicated device, so it will have more advanced secondary effects to worry about, as you can imagine. So that's why we have dedicated models, and there are other models as well. Different researchers and engineers over time propose different ways to represent BJT properties with basic circuit components. So these two models are the most popular, Ebers-Moore model and hybrid pi model. And turns out for different modes of operation of the BJT, one of these models would be better than the other. For example, this model, Ebers-Moore model, is better for switching applications, where you are switching from cutoff to saturation, say, or on to off to on. But the hybrid pi equivalent circuit model is it better describes the device for amplification applications, okay, because it considers the parasitics very well. I'm not going to the detail of any of this and the way of deriving any of this. This is a high level overview anyways, because you don't need to memorize any of this. It's a really old concept. Just wanted to have one slide to show you some of the recent device equivalent circuits. Both of these were proposed and invented by my group. One is for ferroelectric capacitor. I just want to highlight the complexity. Notice there are many components necessary to describe a ferroelectric capacitor, which is another device. Think of a superconducting tunnel junction, which also known as Josephson junction, which are used to make quantum qubits for quantum computers. Okay, so this is an equivalent circuit model for Josephson junction, and multiple components are coupled together, as you see. So equivalent circuits could be developed from ground up. Doesn't matter whether it's for a BJT or a diode or a MOSFET or any other complicated devices. They have value, but oftentimes they require in-depth mathematical understanding of the device itself. Finally, this is practically the final concept that we'll cover in BJT. This is the time delay factor. So we care about the time it takes to go from emitter through base all the way to collector. That directly translates into the speed of the BJT. And wanted to show you, this is the time or transit time from emitter to collector. So it is basically divided into 4 factors. There are 4 factors at play that determines the overall speed. Number 1 is tau e, which is connected to capacitive components in the base emitter junction. So remember that you're going from emitter, base to collector. So you have to first go through the base emitter junction. Okay, so this is where the first component comes in. And these capacitances are related to the junction capacitance. The second one is the base transport time or transit time. So after you have come to the base terminal, how long does it take to diffuse through the base and get to the base collector junction? This time is represented as tau b, and it is related to the diffusion coefficient within the base region and the width of the base region. As you can imagine, if the base is wider, it will take it more time to travel through the base. I'm going to draw it again, emitter base collector. Third one is the collector depletion region transit time. So after it has transited through the base, it will arrive at the base collector junction, and it will take it some time to diffuse through the base collector junction again. So this third component is related to that. The fourth one is the collector capacitance charging time, which is basically the delay within the collector. There are 2 additional parasitic capacitances, capacitive components that we observe at the collector, and they collectively lead to some additional time. Okay, so adding this 4, you could calculate tau EC, which is the emitter collector transit time. And this is an important parameter because it is directly translated to speed as well as frequency response. So what do we mean by that? Notice in this diagram, we are showing the beta, which is basically the related to the amplification capability of a BJT. The higher the beta is, the more amplification you can get out of a BJT. Okay, so you want this to be high. So notice beta remains high up to a certain frequency, which is good. So that means up to this frequency, BJT works just fine. But beyond that frequency, you start losing beta. And at some point, it becomes 0. So when it becomes 0, that's practically the cutoff frequency. Device is no longer going to be useful beyond that. But even before it reaches 0, it starts losing beta. Obviously, you want to make sure your designs are within this zone. They don't even go over the knee point and take a deep dive to 0. You want to make sure that your design stays within this point. So you should try to make sure that these 2 points, if beta cutoff frequency and the actual cutoff frequency, they are pushed towards the right, so that you could have more and more higher frequency operation without losing beta. Okay, so turns out tau EC, the component that we just talked about, this basically determines the cutoff frequency. So if you have higher tau EC, you have lower cutoff frequency, meaning your devices will cut off even before you reach a high frequency operation. So it's probably not going to be that useful, as you can see. Okay, so just keep that in mind. This is another factor that we always use as a performance parameter for BJT because it's related to the speed. So with that, that concludes our discussion and lecture on BJT. Thank you so much for listening.